All right, kiddos, today we're going to talk about enthalpy, which is lesson 4.06. Couple of things to think about, a couple of questions to get your brain going here. Why do you get more heat from a can of gas than from a candle? Why do you get more heat from a campfire than from a candle? If you have the same mass of wood, candle, and gasoline, which would you get more heat from, and why do these things stop burning? You might come away with the idea when you think about those questions that not all substances contain the same amount of heat energy. Any substance or system has a definite amount of thermal energy. The heat content, or the thermal energy content, like right here, the thermal energy content of any system, a candle or a specific amount of gasoline, is called enthalpy. Don't let the word enthalpy scare you. Just replace it with the word heat energy, okay? So heat, right, or enthalpy is the thermal energy, the heat energy content of a chemical or physical system. Enthalpy cannot be measured directly, so we have to use a change in temperature, like when we did our Q equals MC delta T calculations, our specific heat calculations the other day. It's usually represented with a capital H in italics. And enthalpy is measured in terms of change in heat, measured by temperature, between the products and the reactants. So the formula that you use to calculate delta H, which is the change in enthalpy, right? Delta means change, is equal to the enthalpy, or the heat energy, of the products of the reaction minus the enthalpy of the reactants of the reaction. Remember, the reactants are what you start with. Products are what you end with. So it's kind of like final enthalpy minus initial enthalpy, if you want to think of it that way. Exothermic and endothermic reactions are opposite in terms of enthalpy changes. If you consider that the delta H, or the change in enthalpy, is equal to the enthalpy of the products minus the enthalpy of the reactants, then you can conclude the following. An exothermic reaction will have a negative delta H because the products have less enthalpy than the reactants, and an endothermic reaction will have a positive delta H, or change in enthalpy, because the products have more enthalpy than the reactants. The sign of delta H, either positive or negative, tells whether the reaction is exothermic or endothermic. If delta H is negative, the reaction is exothermic. If delta H is positive, the reaction is endothermic. And you can think of it this way. If delta H is negative, a negative sign means there's a loss of something. So if the enthalpy change is negative, that means there is a loss overall of energy, meaning that heat has been lost from the reaction, meaning that heat has been released. And we all know in an exothermic reaction, heat exits the reaction. So the sign of the delta H number will actually be negative. The opposite of that is an endothermic reaction. The delta H would be positive. You have to add heat to the system, right, in an endothermic reaction. So when you're adding heat to the system, heat is being absorbed. That means that the delta H would be positive. So here in lesson 409, I could show you what that looks like as far as delta H being positive or negative. And so in 409 is all about how to write thermochemical equations, and a thermochemical equation is just a chemical equation that also shows the enthalpy of a chemical reaction. So it's going to be your average, everyday chemical equation with this added part here at the end that shows you the change in enthalpy. In other words, the energy difference from when you started the reaction to when the reaction ended. And remember, if delta H is positive, that indicates the reaction was endothermic. Heat was added to the reaction to get the reaction to go. If delta H is negative, that means there was a loss of heat. In other words, heat was released from the system. So this is ammonium nitrate, and you can see here it's solid ammonium nitrate. It decomposes to form ammonium and nitrate ions, and in the process, it uses or takes in 27.7 kilojoules per mole of enthalpy or heat energy. That means it's an endothermic reaction. That means that the surroundings are going to get colder. So this is one of the actual chemical reactions that happens in one of those ice packs. When the ammonium nitrate breaks down, it absorbs 27.7 kilojoules of heat from the pack itself, from the surroundings, and the pack gets colder. This is another example here of an endothermic reaction. Also in an ice pack, ammonium chloride will decompose into ammonium and chloride ions. In the process, it absorbs, notice the positive sign, it absorbs 14.8 kilojoules per mole of heat. Therefore, the ice pack is going to get colder, noted by that positive enthalpy sign. If the change in enthalpy, in other words, the change in the amount of energy from when you started the reaction to when you ended the reaction, it's the difference, right, in the energy of the products and the reactants. If you have a positive sign here, it's endothermic. Energy is absorbed. Positive sign, energy is absorbed. Now, all of these reactions down here, if you notice, the enthalpy sign, delta H, is negative. So all of these reactions down here are exothermic reactions. When the reaction happens, there's a loss of energy. Energy is released from the system. These are all combustion reactions. And we all know that combustion reactions release a lot of heat and light, right? They are extreme examples of exothermic reactions. So here we have 2 moles of liquid gasoline reacting with 25 moles of oxygen, diatomic oxygen in the air, to produce 16 moles of carbon dioxide gas and 18 moles of liquid water. The delta H, the change in enthalpy, is negative 10,941 kilojoules per mole. That's an exothermic reaction, I know, because it's a negative sign. And in the process, almost 11,000 kilojoules of heat energy are released when we get rid of when we combust some gasoline. This is ethanol, also a fuel, C2H5OH, reacts with oxygen in the air to produce carbon dioxide and water. In the process, it releases, and I know it releases energy because of that negative sign, 1,367 kilojoules of heat energy. This is methane. Natural gas combusts in the presence of oxygen to produce carbon dioxide and water. The delta H is negative 890 kilojoules per mole. That means it's exothermic. It's releasing 890 kilojoules of heat energy. And then C3H8 is propane, like in your propane tank in your gas grill, reacts with oxygen in the air to produce carbon dioxide and water. The delta H is negative 2,220 kilojoules per mole. Negative sign means that it's an exothermic reaction. Heat is released, and it is releasing 2,220 kilojoules in that reaction. Couple of things to take note of when you're writing chemical or thermochemical equations. Changes of state contribute to delta H, so that's what we're looking at here in this equation. This is 2 equations that represents the physical process. Now, this isn't a chemical process, but this is a physical process of hydrogen gas reacting with oxygen gas. I guess this is the chemical process here. Hydrogen gas chemically reacting with oxygen gas in the air to produce water, right? So this is the formation of water. Notice it's in vapor form, right? So we have hydrogen gas reacting with oxygen gas to produce water vapor. That G means gas. The delta H, the change in energy from reactant to product, is negative 484 kilojoules. So in the process of hydrogen and oxygen reacting to form 2 moles of liquid water, 484 kilojoules of heat are released. So this is an exothermic reaction. Then if we want to condense that, right, so now we take this water vapor, H2O with a G behind it, and we bring it down here, same thing. Then we're going to take that H2O, that water vapor, and we're going to condense it into liquid water. Notice that L there. So we're just changing the water from a gas to a liquid. We're condensing it. We have to make it colder. In order to make it colder, you have to remove heat. So the process of taking this water vapor and turning it into liquid water releases a further 88 kilojoules of heat. So the total delta H, when you have hydrogen reacting with oxygen, producing liquid water, so we're going all the way through this process to the end product, which is liquid water, it releases a total combined 572 kilojoules of heat. If you add that up, you get minus 572. When a reaction is reversible, in other words, can go in the opposite direction, product to reactant, the delta H of the reverse reaction has the same value as, but the opposite sign of the forward reaction. If you multiply a chemical equation by some factor, then you must also multiply the delta H by the same factor. So if I multiplied through here, let's say I multiplied everything by 2, right? So if I did this, let me get my pen here. If I multiplied through this whole equation by 2, that means I have to multiply everything by 2. So this would become 4H2 plus 2O2 yields 4H2O. And then I have to also multiply my 484 by 2. So what would that be? 768. So if you multiply, the rest of the equation by 2, you have to multiply the delta H by 2 as well. That would be a negative sign. And then chemists determine most, I meant to use my laser pointer. Chemists determine most delta H, change in enthalpy, under standardized conditions, which is 100 kilopascal of pressure and 0 degrees Celsius for temperature. The change in enthalpy under standard conditions has the symbol delta H with the superscript on the H as a tiny little 0 or naught sign. So if you just see that little naught sign, don't worry about it. Don't let it scare you. It just means that that condition was measured under 100 kilopascal of pressure and 0 degrees Celsius. So in conclusion, thermochemical equations show obviously the reactants and the products in the equation, what you start with, what you end with. They can be endothermic, which means you're going to have a positive number at the end of the equation. The delta H will be written positive, or exothermic, meaning there's a release of heat or a loss of heat from the system, and so delta H will be negative.